Hello, and welcome to Lecture 24 on the topic of mirrors, and specifically images formed by mirrors. So, this is one of three lectures that cover images, which are part of the broader module on optics in general. So, the thinking about light, how does light behave? But these three lectures, all about images, are so closely related that it's very important that you watch all three lectures, that you consider the similarities between them. The lecture that came before this, lecture 23, was on images formed by refraction. That's where I introduced some important concepts like real image and virtual image. So if you haven't seen that lecture, please check it out, at least the key terms, so you're in good standing here. And you also want to take a look at the key formulas because this thing called sign conventions is so important between these systems, okay? Well, let's move on to mirrors and talk about what's going on with images formed by mirrors. We got three objectives. So objective number one, learn the key terms of image formation using ray optics, okay? So then we want to learn the rules such as variable sign conventions specifically for mirrors, and we want to understand why planar, spherical concave, and spherically convex mirrors form images of different kinds. And as far as that understanding, I think we're really going to get there best by drawing these things called ray diagrams. Again, you would have seen those already in lecture 23, but here they're a bit more detailed, actually quite a bit more detailed, and have some very specific rules, which are both elegant and simplified. And when I say that, because that's going to give us an understanding of where we expect images to form, whether those images are real or virtual. What we're not going to do is actually show the derivation behind the formulas, and these are basically the same formulas you saw in lecture 23. It comes down to coming up with some triangle arguments and geometry and some small angle approximations. But suffice to say that the formulas are reasonable because they give the same answers as the ray diagrams do, which themselves are reasonable. So that's kind of the understanding we have, the confirmation through finding out where those images must be. But we'll see that in practice. So let's get to it. Okay? So our key terms. Now again, already defined virtual and real image. I will talk about it quite a bit. But in terms of the relevant key terms for this lecture, planar mirror, convex mirror, concave mirror, and the principal rays. Okay, now I just want to highlight this, and we'll get to it in a second, because we did not talk about this in lecture 23. When we did images formed by refraction, there weren't principal rays, because as I said, the ray diagrams for those are actually the hardest to draw. The ray diagrams for mirrors, and in the next lecture, thin lenses, are very well defined. We have these very specific rules, and they come down to the principal rays. All right, so that's kind of a teaser of an important thing to come. But let's define our types of mirrors, okay? So planar mirror is a flat mirror, like a mirror in your bathroom, okay? On a garage door, whatever it may be. So anyway, so the flat mirrors have no curvature at all. They're flat, all right? So there's some big consequences of flat mirrors. They're really easy to deal with. We don't really have many examples that involve them, right? Very straightforward. They always form virtual images, all right? And those virtual images are always upright because virtual images are always upright, okay? Those two things go hand in hand. Upright means virtual, virtual means upright, all right? And that's every time. No matter where you put your object, you're always going to get a virtual upright image, okay? The image is always the same distance as the object, okay? So S prime equals S, all right? And there's no magnification. The image is neither smaller nor larger than the object, okay? So planar mirrors don't have that funhouse mirror effect where you look shorter or stretched out, because that weird effect of images looking compressed or stretched is for convex and concave mirrors, mirrors that bend out or bend inward, okay? But for flat mirrors, definitely no magnification, equal distance. Okay, so let's get on to the funhouse mirrors, convex and concave. Okay, so convex mirrors are mirrors with circular curvature that curve outward. So the convex part just means curves out. As far as the circular part, we assume that, okay? We're not talking about parabolic curvatures or any other type of curvature. It's always assumed to be circular. That's built into the derivation, built into the simplified results we have of having a center and having a focal point, all right? All right, so convex mirrors form virtual upright images every time. So just like planar mirrors, except now we have variable magnification, all right? So the image can be, well, always be smaller, but we'll talk about why that is. The distance to and magnification of the image is determined by the focal length of the mirror. All right, so I hinted at the fact that the magnification will always be smaller, but definitely varies, right? We can have a lot of magnification in terms of the image being much smaller or only a little bit smaller, and it all depends on the focal length. That's how bent the mirror is, like how curved it is, and where the object is located, okay? All right, so then on to concave mirrors. These are mirrors that are curved inward, again, soon to be circular, okay? And what's cool about concave mirrors is they can form both virtual upright and real inverted images. Okay, so they do both. Concave mirrors are variable. They're utilitarian. They can form all different types of images. All right, and it depends on whether the object is inside or outside the focal point, and we'll see which is which. So I don't want to just give you that rule just yet, but you'll soon see what it is, whether you get a virtual image and you put the object inside the focal point, or you get a virtual image and you put the object outside the focal point, right? And where the real images occur. We're going to see that, come up with the ray diagrams, get a sense for it, right? So now, those ray diagrams I keep hinting at are all based on the principal rays because it's a connect the dots sort of thing. It allows us to actually draw the rays correctly and then use where those rays cross or would have crossed to get our image location. That's what it's all about, all right? So it's not going to give us an exact numerical answer, but it's a way to check your work and have a sense and understanding of this optical phenomenon. All right, so there's three of them. Now technically there's four. There's a fourth principal ray, passes through the center of curvature. It doesn't apply to thin lenses. It only applies to mirrors. So here I've decided to focus on the three principal rays that apply to both this lecture 24 and lecture 25 because they'll be the same three principal rays for thin lenses. Okay. So that's all I'm getting at here is that there technically is a fourth one, but we're going to leave it out, just not that important, not super relevant. Okay? So the three principal rays in any order, but I've ordered them this way. Number one is a ray that passes through the center of the mirror and optical axis, and it follows the law of reflection, where the angle of incidence equals the angle of reflection. Okay? So that principal ray, technically the hardest to draw, because to draw it accurately, you have to use a protractor, but it would pass through the center of the mirror and optical axis. What do I mean by that? Well, here's an example of a convex mirror curved outwards. There's the optical axis, just like we saw with images formed by refraction, where those two lines meet, the curve of the mirror and the optical axis, that's the center, all right? It's the intersection, all right? And so that's the principal ray that's gonna meet at that point, okay? Principal ray number two. It comes in parallel to the optical axis on incidence, so it comes in, right? And then is reflected through the focal point, okay? So parallel in, reflected through the focal point. Then the third one is just the opposite of that. It comes in through the focal point, so incident through the focal point, and is reflected parallel, see? All right, and that has to be the case. If there's one, the other one must exist, okay? So that's great to have a description of the three, but let's see what they look like, right? So that's really the way to see them, to actually see an image of them. So I'm going to do it for both types of mirrors, for our concave and our convex cases, all right? So let's go ahead and start with our convex, all right? The one that only forms the virtual images, apparently, okay? So let's go ahead and take a look at an example object. Well, first of all, I want to say something important about convex mirrors is by definition, convex mirrors always have negative focal lengths. What does that mean? Well, you saw a bit about sign conventions in lecture 23, but just hold on to that idea for a couple minutes because I'm going to carefully define what I mean by always having a negative focal length. Okay, now every mirror has a center of the circle, which is the center of curvature, point C, and every mirror has a focal length, which is 1/2 the radius of curvature. So it's half the distance to here as it is to the point C, right? So point F is the focal point, and the distance to the focal length comes from this here, okay? All right, and in fact, you can see I wrote in F, the focal length shown there. I also wrote in some other distances, S prime, that's the distance to the image, S, which is the distance to the object, again, always measured from that intersection, okay? And the three principal rays are shown. I'm not gonna get into too much about the principal rays here. I'm gonna be doing that in an example. Well, actually a question, a concept question, just in a few minutes. But take note, they're all here, right? 1, 2, and 3, following all the same rules. And in this case, we got our image. Our image is virtual, all right, and it's upright, okay? Let's just take a look at the three principal rays for a concave mirror, though. All right, so here's our concave mirror. Concave mirrors always have a positive focal length. And hinting at that sign convention, notice that here the focal length was drawn inside the mirror. On the opposite side is the object. And here, notice that the focal point is drawn over there, which is on the same side as the object. That has something to do with the whole positive negative business, okay? I included all three of the rays, the principal rays. We got the distance to the object S and the distance to the image S prime, okay? So they're the principal rays. Notice there's a lot less going on here. It's a lot easier to draw these principal rays for the concave mirror. Notice that this is a real image. It's real and inverted, all right? So, things to take note of. Okay, let's go down and take a look at our key formulas. Basically the same formulas we saw for lecture 23 and the same formulas we're going to see for lecture 25. That's both good and bad because that means we have the same formulas for these three different cases: refractive images, mirror images, and thin lens images. However, these formulas all apply slightly differently to those three systems. So that's what you got to be careful about. And that's what I always stress. Okay, so let's just take a look at them. All right, so S is just the distance to the object. Okay, you saw that in the figures above. Saw in lecture 23. S prime is the distance to the image. Okay, all right, excellent. Here, M is the magnification factor, all right? Magnification factor by definition is always equal to negative S prime over S. Interesting, okay? And here, this top formula is very specific because look, M is equal to 1. Well, that only applies to planar mirrors. So that means this whole line, this row of equation, is only for planar mirrors. And how else do we know that? We'll look at the sum of 1 over S and 1 over S prime. Well, it equals 0. That's also unique to planar mirrors because planar mirrors don't have a focal point because they don't have a radius. The radius is effectively, not greater than infinity, but it's effectively equal to infinity. It's like it's so not curved, it's flat. And that means no defined focal point. Makes the equation look like this. All right. Notice too, if you solve this equation, you get that S equals S prime, which is one of the conditions of a planar mirror. All right, good. We don't really use this much, but we certainly use this next row a lot. All right, so let's take a look at that. Now in this next row, I want to be careful with our sign conventions, and that would have applied to planar mirrors too. Again, just doesn't come up. But sign conventions, okay? So they're all based on S, where the object is, because if the image is on the same side as the object, that is defined as positive, okay? Both for F and for S prime. But if the image is on the opposite side of the object, then we're going to have a negative S prime, see, negative. And if the focal point is on the opposite side of the object, then we have by definition a negative focal point. Now, as far as the focal point sign conventions, these two here, they're really locked in with the two types of mirrors because we say that the focal point is always kind of inside of the curvature, which means that all convex mirrors have negative focal points, negative focal lengths, and all concave mirrors have positive focal lengths, okay? Because they're always have to be on the same side as S, okay? Now, S prime isn't locked into mirror type because obviously concave mirrors can form both positive and negative S primes because they can form both real and virtual images, okay? And which of these signs corresponds to real? Yep, the one that is on the opposite side is going to be virtual, so actually not real. So opposite side is virtual, and real is on the same side. So positive means real, all right? Well, at least for S prime, it means real, okay? Interesting. Okay, so positive means real. But there's another way to tell if an image is real, and that's if it's inverted, which means it has a negative magnification. And these are the sign conventions. You guys stick to me. There's no reason to be like, wait, why does negative M mean real image? It just does. It means that all real images are inverted. Okay? And the M, really, the negative, you should think, okay, flipped upside down, it makes sense that's defined as negative. It doesn't have to be, but that's the way that we do it. Okay, that's the convention. All right. So anyway, here's the formula, right? The rewritten image formula, but here not equal to 0, but instead equal to 1 over F for the focal length. Okay. And we can also say that the sum of 1 over S and 1 over S prime is equal to 2 over R. Well, why is that? Well, that's just because R equals 2F. So if I just substitution, get rid of F, replace it with R, then my 1 over F becomes 2 over R. Okay. All right, so that's just another way of writing it. Maybe you want to solve for the radius or something. I have an example like that near the end of this lecture. Okay, and there's that magnification, always by definition equal to the negative of the image distance over the object distance, okay? All right, so as far as the conventions for magnification, you know what's so cool? Is although we have to worry about whether if something's on the same side, does that mean it's positive or that means it's negative? Well, you don't have to worry about that with magnification because magnification always means the same thing. Whether you're talking about images formed by refraction, images formed by mirrors, or images formed by thin lenses, magnification is always defined the same. And that's so important because I didn't say this a minute ago, but what stands out about this table, especially compared to lecture 23, which I assumed you watched before this, is these are the exact opposite, right? Before, a positive S was on the opposite side, or excuse me, a positive S prime was on the opposite side of S. Ah, why was that? Well, that's because when real images formed by refraction were formed inside the refractive material, and it was transparent. So that made sense that the real image would be formed inside of the glass rod with a curved edge, which was kind of the canonical example, right? But here you can't form a real image inside the mirror. No light can go in there. There's a wall behind the mirror. Okay, so it makes sense to put the positive on the same side. So there is a logic that follows. Okay, and that logic is tied in, locked in with the magnification, that universal rule. And what is it? To quickly run through it, positive magnification always corresponds to upright virtual images. Okay, always upright, must be virtual. Negative magnification means it's flipped upside down, so it's inverted, which means it must be real. Now, magnification can also be greater than or less than 1, right? If it's less than 1, it's smaller, right? That's an image that's shrunk relative to the object. And if the magnification is greater than 1, well, that's an image that's blowing up. It's stretched out, okay? All right, let's do some examples. I think we're definitely ready, okay? Only one type of problem here. Just problems involve virtual or real images formed by mirrors, especially circular curved mirrors, all right? Which by especially, I mean like 99% of the time. All right, so example 1, we're just going to run through some cases here, just moving an object around, and this will be our one case where we start with a planar mirror for comparison. So a person with a height of 1.54 meters stands in front of a flat mirror, okay? They are standing 1 meter in front of the mirror. What kind of image do they see in the mirror? How far does that image appear from them? And what is their height in the mirror? All right, great. Well, here's the picture, right? Here's the object, which is the person, standing a distance S in front of a mirror, which is this vertical black line. They have a height H. Here's their image with the image distance and the height, right? Doesn't it look like S equals S prime and H equals H prime? Well, it sure does because they should. All right, so they see a virtual upright image. We know that without any equations because that's always the case for flat planar mirrors. We know that S has to equal S prime because there's no focal point, so there can be no change. All right, so that means that the distance is 1 meter, distance from the meter, from the mirror, that is. I guess if you wanted to find the distance from the person, it'd be S plus S prime. So technically the image is 2 meters away from them, all right? And H equals H prime, or H prime equals H, which is just 1.54 as stated, all right? And one thing that is important, a good thing to remember, is that, of course, the way to find magnification is negative S prime over S. But what does magnification mean? It means, what factor, it's dimensionless, it's just by what factor is the image height compared to the object height. So, of course, H equals M times H prime equals M times H, right? So the image height is just the magnification factor times the object height, right? So you can definitely say then that M is just going to be equal to H prime over H, right? Just another way of thinking about M. It's good to remember that as a good reality check. And that's, of course, what I'm using here. Okay, so now on to the interesting case. Now the mirror is switched without the person or their distance from the mirror changing. So in other words, H and S are unchanged. Okay, so the flat mirror is replaced with the concave mirror with a radius of 3.05 meters. Then what are the image type, distance, that'd be S prime, and height, that's H prime, of the image? Okay, so let's see. All right, so now we still have our same S and our same H. We have an F now, okay? F defined like this because it's a concave mirror, so F is defined on the same side as the object. That's a positive F, all right? So I'm going to show you that we're going to get a negative S prime, all right, and a positive H prime, which tells me my image must be virtual because it's being formed inside of the mirror, okay? Virtual and upright. Okay, but why? Why is that the case? Well, let's just work it out. So we'll start with the formula, all right? So we're going to go ahead and solve for S prime. I just want to quickly show this math here. So if I wanted to isolate S prime, I would start by subtracting 1 over S from both sides. So I'd end up with 1 over S prime equals 1 over F minus 1 over S. I want to get S prime by itself, so I'm just going to raise both sides to the power of -1. It's a quick way of doing it. And if I do that, obviously this 1 over S prime raised to the power of -1 just becomes S prime. So then I just have my result that I have 1 over S minus, or 1 over F minus 1 over S to the -1 power is equal to S prime, which I wrote right here. All right, I'm going to plug in my numbers because I know F to be 1.525 meters, and that's because that is 1/2 of R, right? And I was given R, so all I've done here is just find F by taking my value divided by 2. My S is still 1 meters like it was in part A, and there we go. We get a negative value for S prime, negative 2.9 meters. So definitely larger than S, right? So the image is further from the mirror than the object is from the mirror. Negative. Negative. It's inside the mirror, which means it must be virtual, okay? The image must be virtual. Anytime you have a negative S prime, that means a virtual image, all right? And we can go ahead and find the magnification, plug in the magnification, and the thing about the magnification formula is it's written this way with the negative specifically to tell us if the image is upright or not. Because when we plug in that negative S prime, our negatives cancel, which means we end up with a positive value of M, which tells us our image is upright, as it should be for virtual images, all right? These are locked together. Okay, so this is really just confirming it. Okay, all right, so finally then, let's do it for the convex mirror, all right? And well, first, one thing I asked for is not just the magnification factor itself, but the new height. So here, that's really just one extra little step. I just took the magnification factor multiplied by the original height to find out this is how tall the image is, right? It's 4.47 meters tall, so real stretched out. All right, okay, so here we have the convex one. Now we know the convex is going to form virtual. There's no ambiguity there because convex mirrors can only form virtual, right? We don't know, what it's going to be like. It turns out that it's going to be closer to the mirror. So you can see here that S prime is actually smaller than S, as before S prime with the concave one, S prime is larger than S, okay? But it's going to be same image type. See, both cases we're getting virtual images, just different types of mirrors giving us virtual images, okay? So let's see, notice F, right, look at that. All right, so here's the formula, right? Same thing, same, right? I'm just saying now I'm just going to start right with it because yeah, every time technically you start this formula, but so often our unknown, the thing we want to find is the image distance. So this is like kind of a prefabricated version of that formula, just solved for S prime. Plug in my numbers. Look at this though, right? It's the same mirror in terms of the curvature, but now F is negative, right? And that makes all the difference because when I plug in that negative value and everything else, my same value of S, and I solve for S prime, I get a different number now, obviously, right? And it's smaller. It's still negative, right? Just like as I got in part B, but now it's smaller than 1 rather than larger than 1. So if I solve for the magnification, I get it's upright, but it's only 0.6 meters tall. See? Oh, that should have units too, because this is, oh no, this one doesn't have units yet. But the factor is 0.6, so it's 60% as tall. So then if I plug it in, I find that the image is less than a meter tall, because it's only 60% as tall as the object, okay? Multiplied by 0.604, right, by the original height, okay? So, and the type then, definitely virtual upright, okay? Again, so think what I did here, right? One thing is I didn't draw any ray diagrams yet. We're going to be talking about that in just a moment. I wanted to just start by getting some intuition where S and S prime are for these different cases. And I showed that we can definitely get virtual images with both types of mirrors. Okay, so I'm really kind of highlighting the versatility of the concave mirror. But but they don't form the same type of virtual image. It seems like this concave mirror likes to form magnified in the sense of larger images, whereas the convex mirror forms these shrunk down images. Okay, it's actually might be consistent with your experience at a fun house, right? That we think about which one makes you look shorter, which one makes you look taller, right? In terms of the concave and convex mirrors. Okay, so now let's do ray tracing. So not just drawing the relative sides of the mirror and relative lengths of S prime and F and all that. Let's do the principal rays. Let's walk through them. All right, so we're gonna do the principal rays for two cases, both for concave mirrors. And you guessed it, this is gonna show the cases for this concave mirror where the object's relative location to the focal length is going to change the image type. So it's going to cement that rule of when we get virtual images for concave mirrors and when we get real images for concave mirrors. Okay? All right, so first of all, in the first one, we're just going to draw the principal rays. Here we have an object inside the focal point, concave mirror, optical axis, center of curvature. We got it all. Okay? So we'll do our three principal rays. Start with the first one, right? Again, most difficult one to draw accurately because you got to get a protractor, right? But here we have, comes in, follows the angle, the angle of incidence equals angle of reflection rule, the law of reflection. Okay, so first ray. Second one comes in parallel, gets reflected through the focal point. Good, straightforward enough. Third one. Well, the third one's supposed to come in through the focal point and then get reflected parallel. But what happens when your object is inside the focal point? You can't have a ray go backwards, right? Because we really care about, these principal rays are just the three that we choose. There's an infinite number of rays that are emanating from this object. These are just three that highlight where they cross and thus allow us to find the image. But anyway, so this one, has to be going off towards the mirror, in the direction of the mirror, but it can't go through the focal point. Well, what you do is you imagine if it had come from the focal point. So that's why I drew this dotted line, because this is showing like where the ray would have come from. And that then helps me draw the ray so that it's going in the right direction and then gets reflected parallel. Okay? All right, so that's principal ray number 3. Okay, now these are divergent rays. They're divergent because look, they're spreading out. They're never going to cross, right? If we just continue these rays for infinity, they will never cross. So what we need to do is draw extensions of the diverging rays because they do have a common origin. All right. And you remember the thing about virtual images? They're the type of image that we can see without reflection or further, like processing of that image. That are we naturally see virtual images because our brain, kind of extrapolates where those rays are coming from, seeing that common origin, and that's where it appears. All right. So that's the idea. The extension of the diverging rays tells us where that virtual image would appear to the human eye. Okay. And there it is. There is our virtual upright image. Okay. And see how, again, the way I extended all the diverging rays, I extended them after the reflection. So it's really important. You don't extend the incident rays. You extend the diverging reflected rays. See, that's why this one that got reflected parallel, its extension was parallel, and so on. Okay. All right. So there we go. We got our virtual image done with ray tracing or a ray diagram. Let's do it for this case. The only thing that's different now is the object is outside the focal point. It's also outside the center of curvature, but the important thing is outside the focal point, right? Principal ray number 1. Principal ray number 2, parallel, reflected through. Principal ray number 3, through F, and then reflected parallel. Okay? Well, do they cross? Absolutely. So these are converging rays. We don't need to think about any extensions because they're crossing. They're forming an image, a real image, right? If I put a piece of Polaroid, photoactive paper here, it would actually activate because there's photons, there's energy, okay? There's no energy here. But also we couldn't see this image because this would be a real image. Your eye can't see a real image because the light then is just going off in all directions and you never know that the light passed through here. There's no way for your brain to extrapolate the location of this because it's already happened. And then now, look, this light's just going to continue on its way. Right? Much of that light won't make it to your eye. Okay? All right. So here's our real inverted image. All right. All done with ray tracing, principal rays. Okay? And do you see the rule? Okay? The rule is that we have the virtual image formed when the object is inside the focal point, and we have the real image formed when the object is outside the focal point. This highlights the two ways that images are formed for concave mirrors. Okay. All right. So let's take a look at another ray tracing problem or example here in example 2. All right. This one I did it a little bit faster, right? I didn't do as many, but I wanted to show that for this concave mirror, we're getting a virtual image. Okay, shrunk down. See, little small virtual image, and the principal rays all drawn in here. Principal ray 1. See, principal ray 2 is this one here. Okay. And then actually principal ray 2 would come in parallel, so it's this one, and then get reflected, okay? And principal ray 3, the one that wants to go through the focal point, comes in like this, and then gets reflected parallel. And you might be like, how is this principal ray 3, the one that comes through the focal point? Like this ray comes in like this, doesn't go through the focal point, but look, it would have had it continued, because look, if it continues in, it hits the focal point. So we just say, okay, if it was allowed to continue, then it would hit the focal point. So then it must get reflected parallel, right? It's principal ray number 3. And these are all the extensions of the divergent rays. And then we see where they cross is that virtual image location, okay? All right, but we're doing more in this problem than just drawing ray diagrams. We're moving an object. We're gonna have an object initially at S1, and we're gonna move to S2, right? Just gonna move the distance of the object, okay? So an object that is h tall, just a placeholder because we'll never solve for the actual height, is placed with its base along the optical axis of a spherical convex mirror with a focal length of 4.5 centimeters. The object is moved from a position of S1, which is focal length plus 3 centimeters, to a final position of S2, which is focal length minus 3 centimeters. So in other words, it's going to be moved from, well, 3 plus 4.5, 7.5, down to 4.5 minus 3, 1.5. See? So it's moved from S1 equals 7.5 centimeters to S2 equals 1.5 centimeters. Okay? But what's cool is it's moving equal distance about the focal point. By what factor does the magnitude of the magnification of the image change? And does the type of the image change? You might be able to answer that already. Okay? All right. So here's our familiar formula. Go ahead and solve for image. Okay? Image distance. Plug in our values. Okay? Notice it's negative focal point because it's a convex mirror. And we get negative 2.81. Right? That's this distance right here. This would be S1 prime. Good, okay? Well, should we do that again? Absolutely, right? All we're gonna do is just move it. So after moving, we're gonna have a new image, S2 prime, plug in the value, same focal point. The only difference here is a much smaller value of S, okay, because it's S2 now. All right, and then we get our new S2 prime, our new image location, negative 1.13. Oh, interesting, okay? So what happened then? Well, we can then compare the magnifications, okay? So for example, M2 is negative S2 prime over S2, okay? M1 is negative S1 prime over S1. Well, so what I've done here is, since they're both negatives, both the M expressions, and I'm they have a ratio on magnifications, the negatives cancel out, which is why you don't see it here. See, negative's gone. And I'm multiplying by the reciprocal, because notice here, this is just M2, right? So with the cancel negative. And then this is, since I'm dividing by M1, this is 1 over M1, right? That's why we have the image on the bottom and the object on the top, okay? Okay, nothing cancels here because these are all different 4 unique numbers. Plug everything in. We're going to have the negatives cancel one more time, because when I plug in my values of S2 prime and S1 prime, the image distances, they're both negative by definition, right? Because they're both forming on the opposite side of the mirror from the object. Anyway, so the the negatives cancel out. And so then we just plug in all these numbers, and look what we get. Exactly 2, the integer 2. Because we move the object symmetrically about a focal point, we have an integer value of magnification. We have a nice clean change in magnification. Okay, and that's the case when you move it like this. Okay, and you can see why that is if you plug everything in and do some nice algebra and see what simplifies. Okay, it's pretty cool. Okay, so did the type change? No, absolutely not. Right? The image type didn't change. You might be like, well, hold on, shouldn't we do the ray tracing and find the virtual image, once the object is over here, right? Should we do this again? Well, no reason to, because this is a convex mirror. What type of image do convex mirrors form? Virtual, upright, every time, right? The image type stays the same because convex mirrors can only create upright virtual images. End of story. Okay, so let's think about some special cases about mirrors, because we did a lot of cases moving the object relative to the focal point around and seeing the trends, when things are magnified a certain way, when they're upright, when they're inverted, all that. Okay, but what about when the special cases? What about when you put the object exactly at the focal point? Or what if you put the object so far away that the rays are all coming in parallel? Right? These are important questions. They're gonna apply to systems like microscopes and telescopes, and they're just good ways to get a handle on the overall rules, the big questions. So let's look at that. I think that's my goal of these 2 concept questions. So concept question 2: if an object is placed at the focal point of a concave mirror, where will the image be formed? Okay, so we'd have a concave mirror, we've got a focal point, and I'm gonna put my object right there. How would you follow the rules of ray tracing in that case? Well, you'd find that they wouldn't work very well, because it turns out that what you get is you get an image at an infinite distance. Okay, now you can try these with ray tracing. It's a good way to get a handle on it. But I'd say there's a good argument to be made by saying, okay, well, we've got a formula that always matches the ray tracing. Let's then just think about what it means to plug in S equals F into that formula. So here's the formula. Here's the idea. Because we're setting S equals F. We're saying we're putting the object exactly at the focal point. Well, if you do that, think what happens to the equation. Their 1 over S becomes 1 over F, which means now we have a 1 over F on both sides of the equation, and they cancel, which means 1 over S prime, 1 over the image distance, has to be equal to 0. Oh, well, that's a weird statement, because that's only true if S prime equals infinity. So sure enough, if you put an object exactly at the focal point, you don't get an image. All right. What it look like in real life is blurry, right? It'd be out of focus. You wouldn't be able to resolve a clear image if you put the object at the focal point. All right. Kind of cool. Okay, so one thing you might hear a lot about, this idea of the focal point, is that there's a lot of energy there. It's focused, right? After all, it's called the focal point. And maybe you've heard of this idea of cooking on a big mirror, right? By putting something right at the focal point of that large mirror on a really bright sunny day, and all that sunlight then gets focused there, and there's so much heat that you could actually cook food at that focal point. Now, often that's sort of a parabolic mirror, but the principle is the same. So why is that then? Why is there so much light passing through the focal point? Because it's not like we're seeing our images always form at the focal points, right? Here we had a virtual image, didn't form at the focal point. Back here, we had a real image, did not form at the focal point. So, obviously it's not like the focal point is the end of the story. You can have images form in lots of places. But there is a very common case where the image does form at the focal point. and that's for objects that are far away. So if light from a very distant object arrives at a convex mirror, where will the image form? All right. Well, at the focal point, because when s is set to infinity, and think what the formula becomes, right? This formula right here, it simplifies to just 1 over s prime equals 1 over f, because s equals infinity, this goes to 0, right? 1 divided by infinity is 0, which means that s prime equals the focal point. The image equals the focal length, all right? And that means the image would be virtual and upright, right? Which is always true of convex mirrors, but all the light would be focused right there at the focal point. The idea is that the rays would all come in parallel. There's all the 3 incident rays. There's no principal rays because they're all parallel. And they're all just then going to focus in on that one focal point, okay? Okay, what about for a concave mirror? Well, for a concave mirror, you're going to also get an image at the focal point, because the same equation applies, all the same logic, but this time it's going to be real and inverted, all right? Now, it would also be infinitely small, because in this case, right, they all come in like this. Here are your principal rays, and they're all just going to focus back in on that focal point, all right? There is your focal point, F. They all focus on that one point. All right. Again, the image would be infinitely small if you actually worked it out, right? But all the light would be focused at that single point. All right. Okay. So I bring this up because actually, interestingly, in example 3 and example 4, we're going to be looking at concave mirrors and convex mirrors, but these are actually both cases where S prime approximately equals F, right? So it's kind of interesting. These are 2 applications of that idea of the light coming in and forming at the focal point. Now, it turns out in both cases they're not exactly equal, but they're pretty close, right? Because if your object is just 10 times further from the mirror than the focal length is from the mirror, that's a pretty dramatic change, and that's going to get you pretty close to this idea of S prime almost equaling F, okay? All right, run the numbers, check it out. All right, so let's do these 2 examples. Now, these are kind of just further practice, no fundamentally new ideas here. These would be great ones for you to try yourself and then take a look at my solution and my explanation after you've given them an attempt. Okay, so example 3. A student wishes to create a real image, all right, so there we go, it's gonna be inverted, of a tree using a single concave mirror. The image needs to fit on a small sensor that is 1 millimeter to a side, and the tree is 88 meters tall, right, and is located at a distance of 310 meters from the mirror. All right, what radius does the mirror need in order to make sure the image fits on the sensor, right? So, tiny little digital sensor or something, right? This is some science spirit. How far from the mirror should the sensor be located, right? Okay, so we want h prime to be 1 millimeter. So we're going to set up our equation and solve for magnification, okay? By definition, magnification is image height over object height, h prime over h. We know both those because we're told the tree is 88 meters tall, right? So there we find out that our magnification is really small because we would need that image to be a lot smaller than an object, right? So it's 1.14 hundred thousandths, okay? No dimensions or anything, it's just a factor. So then we're going to take that and use it then to solve for S prime, okay? Because we already know S. We already know that the tree is located 310 meters away. Okay, so I'm going to solve for S prime, right? There's my magnification factor, and there is my S, my distance to the object. So that means that my image distance is 3.52 times 10 to the negative 3, which is 3.52 millimeters, okay? Notice here, though, this is the wrong formula. Where's my negative? Did I leave it off? No, I did not include the negative on purpose, and that's the negative in the formula that relates S prime and S, right, to M, because we do not need the magnification to tell us that the image is real and inverted. Because the formula, this familiar formula, negative, M equals negative S prime over S, the negative there is just the sign convention, all right? It's there to tell us what our image is doing. Its purpose is to tell us if the image is inverted or upright. If you don't care if the image is inverted or upright, then you shouldn't include that negative. Because think if I had included the negative, I would get a value of negative for S prime. But a negative for S prime, by the sign conventions, tells me virtual image. But I know this isn't a virtual image because I specified it to be a real image, all right? So I'd be like double counting the negative, okay? All right. So there are times to include it and times not to, depending on what you're solving for, right? And this is the only time we've ever used this formula to solve for S prime, okay? So now that I have that value of S prime, I can go ahead and plug it into this formula, which instead of being equal to 1 over F is equal to 2 over R, because I want to solve for R. I'm going to use similar algebra to the algebra I explained earlier in this lecture to solve for R. Go ahead and try this yourself. And plug in my numbers, right? And my positive value for S, my positive value for S prime, because, real inverted image, and S is always positive. And what do I get for my value of radius? 7.05 millimeters. So it's got to be a very small mirror, right? Because it's got to focus that light, so tightly onto such a small space. Okay? And then as far as how far from the mirror should the sensor be located, well, let's think about it, right? I want the sensor to be located at S prime, all right? And I already saw for S prime up here as an intermediate step. So I already know it, right? It has to be equal to 3.52 millimeters, that value, right? So I already know it. And what's cool though is notice that 3.52 millimeters is pretty close to 1/2 of 7.05 millimeters, right? So S prime is being formed at approximately the focal length. Because remember, right, R is just equal to 2F, all right? So this basically meets that case where the object is so far away that the image is forming at the focal point, okay? All right, let's take a look at this one. This is a rear view mirror on the passenger side, convex, caved outwards, all right? So the writing on the passenger side of the mirror, mirror of cars, says, warning, objects in the mirror are closer than they appear. There's no such warning in the driver's mirror, right? Why is that? Because it's not curved, right? Consider a typical convex passenger side mirror with a focal length of -80 centimeters. A 1.5 meter tall cyclist on a bicycle is 25 meters from the mirror. You are 1 meter from the mirror, 1 meter from the mirror, and suppose, for simplicity, you all make a straight line. So you're all along that optical axis, right? And just imagine here that this semi-truck is replaced by a bicycle, and we're looking at how far does that bicyclist appear, okay? So let's run through it. How far are you from the image of the cyclist? How far would you have to be from the image if the mirror is flat? What is the image height? And what would the image height have been if the mirror were flat? All right. Okay, so find the distance to the image. Okay, so there's our formula. Okay, plug in negative focal length is convex. Distance to the object, 25 meters is cyclist. Then we get negative 0.78 meters. Okay, so that's the distance to the image. And that's the distance from the mirror to the image, right? So then the distance from the person to the image is the distance from the person to the mirror, 1 meter, plus the distance from the image to the mirror, which is the absolute value of that. So the image from the passenger is 1.78 meters away. Okay, 8, great. Okay, now what about B? Okay, so B for the flat mirror, well, now the image distance has to equal the object distance, so it's 25 meters. Well, that's a lot bigger, all right? And that means the distance from the passenger to the image is 26 meters. Dramatic difference, okay? And then let's think about the magnification, all right? But before we do, let's appreciate this, right? So the distance from the person to the image when the mirror was curved was really small. So the image was close to the passenger. When the mirror was flat, the image was far from the passenger. But yet, it's the curved mirror that makes things look further away than they really are. That seems in contradiction, doesn't it? Well, it must not be the image distance that matters as much. And let's see why that is. Okay, so let's find the magnification. This is the magnification for the curved mirror, right? For the convex mirror. Plug in our value of S prime, which is negative. So the negatives cancel, which they should, because we should get an upright virtual image. And there it is. There's our magnification. Oh, that's a pretty small magnification, right? So it tells us that the height of the image, the height of the bicyclist, is going to be h prime equals mh, so that magnification factor times the original height of the bicyclist is at their actual height, and we find then that the image height is 4.65 centimeters. Well, what about for the flat mirror? Well, for the flat mirror, the magnification is 1, which means that the image height is just equal to the height, so the image is 1.5 meters. Now do you see it? Look. So we have that the person in the convex mirror is really small. Their image is really small, even though they're close. Whereas in the flat mirror, the person is full size, but the image is really far away. So which ends up making them look smaller? Turns out that this does. The fact that they're shrunk down, but still close, means that the actual angular space they take up in your vision, and thus the way our brain reads that as being close or far away, is more dramatic for the convex mirror. They appear further away because of that real small magnification, okay? Even though the image is closer. All right, and to kind of put that in words here, writing, it is not that the image is actually further away, clearly, right? Compare. That makes the object appear further away, but instead, the small size of the image that we interpret as distance, all right? All right, and it does come down to the angular size of the image. Angular size being an idea we'll talk about starting around lecture 27, I think is where it first comes up, so something to look forward to. Okay, so again, consider this lecture in the context of images in general, compare it to everything that you learn in lecture 25, the lecture after this, compare it to what we talked about for refractive images in lecture 23, And I hope it has been a valuable lecture and all this image stuff is interesting. All right, thank you so much for watching.